Chapter 09. Nebular Hypothesis. The story of how our solar system formed begins with a brilliant idea that emerged in the 18th century. This idea, known as the Nebular Hypothesis, attempts to explain how the Sun, Earth, and all the other planets came to exist. The theory didn't appear overnight, but was developed by several brilliant minds over many years. The first person to suggest this idea was Emanuel Swedenborg in 1734. He proposed that our solar system formed from a spinning cloud of gas and dust. 21 years later, in 1755, the famous philosopher Immanuel Kant took this idea further. In his work, called Universal Natural History and Theory of the Heavens, Kant explained that these gas clouds, called nebulae, slowly spin and collapse because of gravity. As they collapse, they flatten into disk shapes that eventually form stars and planets. The theory became even more detailed when Pearson and Laplace worked on it in 1796. Laplace had a slightly different approach, suggested that the Sun originally had a huge, hot atmosphere around it. As this atmosphere cooled down and shrank, it started spinning faster and faster. This spinning motion caused rings of material to break off from the Sun, and these rings eventually came together to form the planets we see today. Laplace's version of the theory was so popular that it dominated scientific thinking about our solar system's origins throughout the entire 19th century. So what exactly does the Nebular Hypothesis tell us about how our solar system formed? The theory explains that everything in our solar system, including the Sun, planets, moons, asteroids, and comets, all came from one giant cloud of gas and dust about 4.6 billion years ago. This enormous cloud, called a nebula, was made mostly of hydrogen and helium, with small amounts of heavier elements that had been created by older stars that had died and exploded. The formation process began when this massive cloud of gas and dust started to collapse inward, because of its own gravity. Something had to trigger this collapse, and scientists believe it might have been shock waves from a nearby exploding star. It's called a supernova, or perhaps the gravitational pull from other stars passing by. Whatever caused it, once the collapse began, amazing things started to happen. As the nebula collapsed and got smaller, something interesting occurred due to a basic law of physics called conservation of angular momentum. Just like when a figure skater pulls their arms in close to their body and spins faster, the collapsing nebula began to rotate more and more quickly. This spinning motion caused the originally round cloud to flatten out into a disk shape, which scientists call a protoplanetary disk. Most of the material in this spinning disk fell toward the center, where it collected to form a dense core called a protostar. As more and more material piled up in the center, the pressure and temperature became incredibly intense. Eventually, these conditions became so extreme that nuclear fusion began to occur in the core. This is the process that makes stars shine, and at this moment, our protostar became the Sun we know today. While the Sun was forming at the center, fascinating processes were happening in the surrounding disk. Tiny particles of dust and ice within the disk began to bump into each other and stick together. Over time, these small clumps grew into bigger and bigger chunks called planetesimals. These planetesimals continued to crash into each other and merge together, gradually growing into what scientists call protoplanets, which eventually became the planets we see today. The temperature in different parts of the disk played a crucial role in determining what kinds of planets formed where. The inner part of the disk, close to the hot young Sun, was much too hot for ice and gases to exist in solid form. Only metals and rocky materials could survive in these high temperatures. This is why the planets closest to the Sun, Mercury, Venus, Earth, and Mars, are all rocky planets made mainly of metal and stone. Further out from the Sun, where the disk was much cooler, ice and gases could freeze and stick together. This allowed much larger planets to form, because there was more material available to build with. These outer regions gave birth to the gas giants, Jupiter and Saturn, as well as the ice giants, Uranus and Neptune. These planets grew so large that they could capture and hold onto thick atmospheres of hydrogen and helium gas. Eventually, the young Sun became powerful enough to clear out the remaining gas and dust from the disk. The Sun's solar wind, which is a stream of charged particles flowing outward from the Sun, blew away all the leftover material. This left behind the solar system we see today, with its planets, moons, asteroids, and comets, all orbiting the Sun in an orderly fashion. Scientists have found many pieces of evidence that support the nebular hypothesis. One of the most convincing pieces of evidence is that all the planets orbit the Sun in the same direction and roughly in the same flat plane, just as we would expect if they all formed from a flattened disk. Another important clue is that while the Sun contains more than 99% of all the mass in our solar system, the planets hold most of the angular momentum, which makes sense if everything formed from a spinning nebula. Modern astronomers have also observed young stars in our galaxy that are surrounded by protoplanetary disks, providing direct evidence that stars and planets do indeed form from rotating disks of gas and dust. Additionally, when scientists analyze the chemical composition of planets, they find that it matches what the nebular hypothesis predicts based on temperature differences in the early solar nebula. While the original version of the theory proposed by Laplace had some problems, particularly in explaining why the planets have so much rotational energy compared to the Sun, modern scientists have refined the theory to address these issues. Today's version, called the Solar Nebular Disk Model, includes more sophisticated understanding of turbulence, magnetic fields, and how particles interact with each other. The nebular hypothesis remains the most widely accepted explanation for how our solar system formed, because it successfully combines fundamental principles of physics, chemistry, and astronomy. It explains not only how our own solar system came to exist, but also helps us understand how other star systems throughout the universe form and evolve. This remarkable theory continues to guide our understanding of planetary formation and the origins of the cosmic neighborhood we call home. Conclusion: the nebular hypothesis stands as one of the most successful theories in astronomy, providing a clear and logical explanation for the formation of our solar system. From its humble beginnings in the 18th century, with Immanuel Swedenborg, Immanuel Kant, and Pierre-Simon Laplace, this theory has evolved into a sophisticated model that accurately describes how stars and planets form from clouds of gas and dust. The theory's strength lies in its ability to explain multiple observations about our solar system, including the orderly arrangement of planetary orbits, the chemical composition of different planets, and the distribution of mass and angular momentum throughout the system. Modern astronomical observations of protoplanetary disks around young stars continue to validate the fundamental principles of the nebular hypothesis, demonstrating that the processes described in the theory are actively occurring throughout the universe. While scientists continue to refine and improve the model with new discoveries and better understanding of physics, the core concepts of the nebular hypothesis remain solid, making it an enduring cornerstone of our understanding of planetary formation and the origins of our cosmic home. Next video, Chapter 10. Summary and the 3 most recognized theories. Thank you for watching. Hope you got a clear idea about nebular hypothesis. If so, please like, subscribe to watch more videos, and share with like minds.